Hello everyone, welcome back in the course of higher surveying, and we are in module 4, error accuracy and adjustments computation. We have already covered one lecture on this module. In that lecture we have seen what is the error, what is accuracy and what is error propagation. Also we have seen that what is a precision, which is generally calculated by standard deviation, and then we have seen what is the difference between the precision, that is standard deviation, and the accuracy. Remember, in order to find out the accuracy, we need to have some kind of condition, and in the last lecture we have given an example of a triangle where we put a condition that the sum of the three angles should be equal to 180 degree, and this condition was independent of the observation. We can calculate the standard deviation from the data, and that is why precision, which is standard deviation, is internal to the data. On the other hand, since the accuracy is calculated by a condition equation which is independent of the data itself or the variable itself, so we said that accuracy is always external to the data. Now we have developed the fundamental concept of error and accuracy, and in the last we have seen what is error propagation. So today we are in lecture 2 and we are going to look into the applications of error propagation. So before we start, we will look some examples of error propagation by the logic or by the formula we have seen in the last lecture. So let us start with that. Okay, so I started a simple example of area of a rectangle, and area is given as a multiplication of x and y. Let us say the length of this room and width of this room, x and y, are measured with some standard deviation value, okay, like this. Okay, now I want to find out what is the value of sigma a, and that is why I have given a simple formula there, that let us see if I want to find out the covariance variance matrix of output, then we will calculate it like this. The J is Jacobian matrix, which is calculated like this. So it is basically 1 by 2 matrix. Okay, what about the sigma xy? It is covariance variance matrix of variable x and y. So it is variance of x, variance of y, covariance of xy, covariance of xy here. So these two elements here and here, they are same, and these two elements, it is variance of y and here it is variance of x. So this is variance covariance matrix, and Jt is nothing but the transpose of J which is nothing but dou A by dou x and dou A by dou y. Now if I write the value here, this value you can write it easily. dA by dx is nothing but y, and dA by dy is equal to x. So this matrix is nothing but y and x. Now if I put all these values, this and this into this, I can get sigma a. A variable is a single variable, so what is the covariance of the variable by variable itself? So we can have only one term that will be equal to the sigma a square, right? The idea here is, if there are two variables, we have covariance, but if there is only one variable, we do not have the covariance. What will I do here? Now I will write sigma a square is yx, sigma x square, sigma y square, and I make it covariance as 0. Why? Because as I know, if the observations are coming from the field, the covariances are generally assumed as 0. So I am assuming that I am measuring the x and y using a tape, so it is a field measurement, and now I can say that covariances are 0 because both x and y are measured independently and they do not influence each other. Their errors are not influencing each other. This is the total matrix here. Now, if I multiply, then what will I get here? Let us say if I multiply first matrix to the second matrix, I will get sigma x square y here, okay, and then I will get sigma y square x here, okay. Then next y and x here. So, I multiplied these two matrices first, okay. What next? Let us multiply these matrices and I will get, I hope you should also get this thing, okay. So, that is sigma a square. You can also find out what is sigma a, that is precision okay. So, what is x and y? They are the measured values in the field, or they are the measured value of room length and room width. Sigma x and sigma y, they are the precision here, and you will look here very carefully that sometimes I measure the length in general one time or two times, but I know from experiences what is value of sigma x. So, I assume the sigma x and I assume the sigma y. Generally, we assume based on the least count of the instrument, that is tape, or if I am using a total station, then I will use the least count of the total station or accuracy of the total station. So, generally we assume sigma x and sigma y and we do not measure it. So, now what I am doing here, I am trying to estimate the error that will be propagated to the area A if I measure the x and y in the field. So, again I am assuming here sigma x and sigma y, and I am trying to find out what could be the error propagated to the area A with these assumed values, and there is a reason to assume it. In fact, I should do, let us say, 100 measurements of length and 100 measurements of width. What is the characteristics of the error of these measurements, and if the random errors are only present, what is the value that is possible for sigma x and sigma y. And so, by this assumption I go ahead. You can take another example. Let us say if there is a radius r and this angle is theta, let us say there is a point, and now what is the length of this arc? Let us see is p. So, p is equal to nothing but r theta. If I measure the angle theta with theta plus minus sigma theta, this is the variance sigma theta, theta is the value in the field, and r is the radius which I measure with sigma r. Okay. So, what should be the value of sigma p by this formula? Sigma r theta jt. Okay. What is the value of j? You can find out. Secondly, you can also assume sigma r theta, since I am measuring the observations directly in the field. So, I can assume 0 values of the covariances. One more exercise is possible. If you assume that covariances are not 0, that means this matrix is sigma square, sigma r theta, sigma theta square, sigma r theta. In that case, what will your answer, or how your answer changes? That means you calculate sigma p and find out. You will get some term with sigma r theta also. So, we have seen two examples here. Okay. Let us take multi-response example. Let us see we are measuring latitude and departure using some measurement. For example, let us say there is a line in the field. Let us call the line AB, and the length is L. Okay. And with respect to the north, I measure the bearing as beta. So, what is departure value here, and what is the latitude value in plane surveying? So, it is L sin beta departure, and it is L cos beta latitude. Fine. So, we write here that latitude equal to L cos beta, departure equal to L sin beta. So, let us see, I am measuring the bearing with a compass and I am measuring the length with the tape. So, Both are independent first of all. Secondly, I can say here that sigma L is precision of the length. So, I am writing the measured length L, sigma L, and the bearing beta as sigma beta. Now, you can see there are only two inputs x and y and giving the area, but here surprisingly we have two responses, one is latitude and one is departure. So, it is called multi-response function. Okay. In that case, how can I find out the propagated error? Let us look into that. Output is sigma LD, and now J sigma L beta JT is my formula. What is the J here? J will be slightly modified now because there are two output variable. So, this is dou capital L by dou L, dou capital L by dou beta. Second row will be dou D by dou L and dou D by dou beta here. And if I calculate the value, you can also do it yourself. It is cos beta, here it will be minus sin beta into L. Okay, what is the second row? Again it is sin beta, and here it will be plus L cos beta. JT, that is transpose of J. So, that is transpose matrix of J. Like this. So, that is it. And what is sigma L beta, which is variance covariance matrix of the input? Again sigma L square, sigma beta square, sigma L beta, I am making a 0 variance covariance. And now, if you find out sigma LD, what should be the size of the sigma LD? Let us look into that. Okay, what is size of J? J is the size of 2 by 2, JT is size of again 2 by 2, it is always 2 by 2. So, if you multiply 3 matrix of 2 by 2, sigma LD will be 2 by 2, and if you try to calculate yourself, you will get an answer like this. Sigma LD is equal to sigma L square, sigma D square, sigma LD and sigma LD here. This is 2 by 2 matrix here. Remember, L and D are dependent variable or they are the response variable, and using the variances of basic measurement, that is length and bearing, I have find out what could be the error propagated in the latitude and departure of a line. Right. So, what should be the value of sigma L square? So, I got some values and I am sharing with you, you also try it yourself. The sigma L square is given by square, that is nothing but the variance of latitude or L. Okay, what about the variance of departure? Given by L square sin square beta sigma L square plus cos square beta into sigma beta square, that is variance of departure or D. Now, what is the covariance? Sigma LD, covariance of L and D. Okay, and this is cos beta sin beta sigma L square minus L square sigma beta square. This is the covariance of L and D, latitude and departure. And remember that I have estimated these values, I have not measured sigma. Okay, so what is the idea here? Remember, we also do the error estimation by other logic, by variation of the parameter, right? For example, if I just draw here the variation of parameter logic for the area A, delta A by A equal to dou A by dou X into delta X plus dou A by dou Y delta Y. Remember, this formula. Okay, what's the idea here? What's the difference there between this error propagation and this error calculation? So this is based on error delta x and delta y. So I'm trying to find out what's the error delta a. But there is an assumption that I'm measuring this delta x and delta y. And so if I know delta x and delta y, and if I can find out delta a, what will I do? Before measurement itself, I will correct a, because I know what could be error in x and y. However, in this case where we are using word sigma precision, I do not know what is the exact error occurring there in the measurement. So I'm making an estimate of that error by sigma L square or sigma beta square or sigma x square or sigma y square, whatever. And using those as estimate, I'm finding out what could be the error of area or in the latitude departure or whatever the dependent variable is. So that is the idea here, right? So don't confuse yourself. What we are doing here is we are trying to estimate the error in the latitude and departure based on estimate of error in the length and the bearing value. And why is it needed? Yes, it is needed in some of the applications. So we'll see the applications of error propagation today itself. These three answers you should verify yourself. Next example is, let us say I have a variable x and I am measuring it as x1, x2, and I am taking its mean, and this is mean, and I want to find out what is sigma x bar here. Suppose it is x bar. So what is sigma x bar? Given x1 is coming from some distribution which is normal, standard deviation plus minus sigma x here. Okay, x2 is coming from some distribution which is normal, but sigma x2 is standard deviation. Similarly, x3 is coming from sigma x3 here, and so on. So xn is coming with sigma xn. That means these are the standard deviation of these values. Okay, let me make a simplification that all these values x1, x2 and xn are independent of each other, and secondly, all the values are coming from one distribution. So I write here sigma x1 equal to sigma x2 equal to sigma xn equal to sigma. That means they are coming from unique distribution, but they are independent of each other. I am just writing it here x1 to xn. If sigma square 0, because covariance will be 0 between x1 and x2, 0 x1 and x3 here, and so on. So then here sigma square, and this is the leading diagonal sigma square, and all are sigma square. Here complete zeros, here complete zeros, and size of this matrix will be n by n. Here I am saying that variance covariance, this value is between sigma x1 2. So my sigma x1 x2 equals to 0, sigma x1 x3 equal to 0, which is this value, and this value 0 is nothing but sigma x1 xn. Similarly, I can write all other values which are equal to 0. So I can say in general that sigma xi, sigma xj is equal to 0. All the covariances between any variable is 0, because all are independent of each other while we measure in the field. Okay, now I want to estimate what is sigma x bar. So use the logic again. Sigma x bar, which is nothing but sigma, this is the way we write, j sigma x1, x2 and xn into jt. Okay, what is J matrix? x1 dou x bar by dou x2 and dou x bar by dou xn. Okay, the matrix size will be 1 row and column, 1 upon n, 1 upon n, 1 upon n, and 1 upon n n times, like this. Check yourself, are you getting it or not? Same way now I can construct the transpose of J, which will be the column matrix. So let us write sigma x bar, which is equal to sigma x bar square, and J matrix, if I write, it will be 1 upon n, 1 upon n, 1 upon n, 1 upon n times here sigma matrix. So, sigma square here 0, 0, here it is up to sigma square, every value is sigma square along the diagonal, and complete these values are 0, right. Then Jt will be 1 upon n, 1 upon n, 1 upon n, 1 upon n. It is n by 1 matrix here, and this is 1 by n matrix here, n by n matrix. So, if you multiply first two matrices, you will get 1 into n size matrix. Then if you multiply 1 into n into 1 size matrix, you will get 1 by 1. So, it is confirming the dimension of this value 1 by 1 here. Okay, so let us multiply. You will get this matrix here. Right, and again this size of this matrix is 1 by n, and here we have this column matrix already, this one. So, it is 1 by n, 1 by n, 1 by n, and so on. Now, if you multiply, you will get sigma square by n square plus sigma square by n square, and these terms are n number of terms. So, I can write here sigma x bar square equal to n times sigma square by n square, and you will get sigma square by n here. What is the value of sigma x bar square? It is nothing but sigma square by n, or I got the value which is here, right. I can write here very easily that sigma x bar equals to plus minus root of this quantity. So, sigma by root n. So, that is the fundamental derivation we do, and we find out that the precision of the mean will be much better because it is much smaller. As we increase n, that will make precision of the mean better. When we take the multiple measurements for a variable, the precision or the confidence is gaining up because precision is reducing there by the factor of root n compared to a single observation that is coming from sigma precision. Okay, let us make this example little complicated and assume that observations are coming from different distributions, which means x1 is coming from sigma x1, x2 is coming from sigma x2, and xn is coming with sigma xn. And although each and every distribution is normally distributed, but all are different. In that case, remember we called weights. We assign in basic surveying some weights, and weights are assigned like this. Say W1 is assigned something like this, W2 is assigned like this for second observation, and so on. So, Wn is assigned like this, and in such cases we find out the weighted average. That means, what is average value here? I call it the weighted average, which is equal to W1 x1 plus W2 x2 plus Wn xn divided by W1 plus W2 and so on, that is summation of weights of all observations. Now, find out what is the mean or the sigma x bar of the weighted average. That is problem now. I made problem little complicated. First I took a simple problem, then I made the problem little complicated. Okay, try to find out. I will also solve here. So, what is sigma xx here? Sigma xx is sigma x1 square, sigma x2 square, sigma xn square. Remember, observations are still coming from the field observation. So, I assume that all covariances are equal to 0, and so whole this matrix elements of diagonal are 0 in both cases. But you can see these distributions are different, and hence all the values are different. Here we are assuming that sigma x1, sigma x2, sigma xn and so on are coming from different normal distributions, right. So, what is J matrix in this case when we write x bar as weighted average here? So, again for simplicity I write here W1 x1 plus W2 x2 Wn xn divided by W1 plus W2 Wn here, right. In that case, what is J matrix? So, J matrix will be dou x bar by dou x2 and so on, dou x bar by dou xn, right. You can differentiate yourself and you can find out that you will get W1 divided by summation of all the weights. So, I am just writing it Wi like this. That is your first member. Here you will get W2 divided by sigma Wi and so on. You will get Wn divided by sigma Wi here. I am not writing I equal to 1 to n, just it is understood here. Why? Because you will see W1 x1 plus W2 x2 and so on, Wn xn here and divided by here Wi I equals to 1 to n, and this quantity which is in the numerator, it is constant, because weights are constants we assume them. So, this is a constant quantity here, because all weights are constant here. Right. So, I know J matrix. You can also derive JT matrix, which is nothing but the transpose of J. Now, we have to plug in all these values into the basic formula. Sigma x bar equals to J sigma x1 x2 xn into Jt here. Okay. Try to find out what is the answer here. W1 upon sigma Wi here, W2 upon sigma W, so on up to Wn, then diagonal matrix which is sigma x1 square, sigma x2 square and so on up to sigma xn square. All the off diagonal elements are 0, and then we have this matrix which is transpose of J. So, if we look the dimensionality, it is n into n matrix, it is n into 1 matrix and it is 1 into 1 matrix. So, if I multiply these 3 matrices, I should get finally one scalar number which is the size of 1 by 1, or I can say sigma x bar here. If I multiply, what will I get? W1 square sigma xn square plus W2 square sigma x2 square and Wn square sigma xn square divided by the square of the sigma w, right. That is why I am writing first in bracket sigma w and the square of the whole quantity. It is not W1 square plus W2 square, no, it is the first we make W1 plus W2 and so on, the complete series, and then the square of that number. So, it is called sigma w whole square, right. So, you get the value of sigma x bar square. So, that is called the error of the weighted mean. Let us check whether this result is correct or not. How can you check it? So, check is very easy. Let us bring back to the same example what we have solved with simplification, where we have assumed sigma x1 equal to sigma x2 equal to sigma x3 equal to sigma xn and equal to sigma. I need to mention here that we have W1 is equal to 1 upon sigma x1 square, and similarly I have any Wi equal to 1 upon sigma xi square, like this. So, here we will see that if I multiply these two, I will get 1. So, basically by multiplying this with this equal to 1, or if I multiply here, I will get here W1. Now, if I put these two values here, so what will I get here? W1 plus W2 and so on, divided by sigma W I, here also I square, and this is nothing but sigma W I divided by sigma W I square, or I will get 1 upon sigma W I. Right, that is final answer. I got it. Okay, so let us see what is the interpretation here. Interpretation is pretty simple, that I got sigma x bar equals to 1 upon root of sigma Wi. So, 1 upon sigma square plus 1 upon sigma square plus 1 upon sigma square equals to nothing but 1 upon under root of n times sigma square, which is nothing but sigma by root n. So, this is check that answers are correct. So, I have also find out what should be the error propagated in the weighted mean, right? And we have checked it also, that if we assume that weights are equal, I will get the same answer what I derived earlier. So, that is the idea here. Now, I will ask you to do a complicated example, okay? And the example is, let us see, in a 3-dimensional coordinate system, using a total station, you measure a distance called rho, and you are measuring two angles. One is the theta in the planimetric, and one is the alpha angle, which is vertical angle for point P, and you are calculating the x, y and z 3D coordinates of point P, and these 3D coordinates are given by in a matrix form by this. It is rho cos alpha cos theta, rho cos alpha into sin theta, and rho sin alpha, right. This is the 3D distance rho here. Alpha is elevation angle with respect to xy plane. Here this is x, this y, and this z. I can write it also, what is my coordinate of point P, xp, yp, zp. What is the value of sigma xp, yp, zp by this formula, sigma rho alpha theta jt, where Jacobian is given by dou xp by dou rho dou xp by dou alpha dou xp by dou theta here. It will be a 3 by 3 matrix here. Second row will be dou yp by dou rho dou yp by dou alpha dou yp by dou theta. Third row will be dou zp by dou rho dou zp by dou alpha dou zp by dou theta here. So, this is a 3 by 3 matrix, and you can calculate it by differential calculus. The equations becoming more complicated. So, the idea is very simple. You can use some automatic tool for this purpose, and the first tool you should use, which is freely available, and that is Microsoft Mathematics. It will help you to write equations. You can write your equations, and then you can differentiate, you can find out Jacobian matrix and so on. You can also put some values if you have, and you can test what is the value of sigma xp yp zp, and the sigma xp yp zp will be 3 by 3 matrix. and that is the exercise you should do using Microsoft Mathematics. It's pretty easy to learn. Okay, let us move to the applications. So first application, we have seen how to find out the errors that will be propagated in the dependent variable. Second application is stepwise propagation. What is stepwise error propagation? What's the meaning here? Let us look into a simple example. I have a series of triangles. I measure this network of triangle is ABC and D, theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6 here. Okay. So, I have measured this distance S and I want to find out what is this distance between C and D. So, I can use sine rule. So, sine rule will give me S upon sine theta 2 equals to, let us say this distance is SAB and this is SBC, fine. So, I can write now SAB upon sine theta 3 and then SBC divided by sine theta 1. I know this distance measured in the field. I can calculate SBC, and again that is equation number 1, triangle BCD. I am writing this equation now, SBC divided by sine theta 6 equal to, let us see, SCD, and this is SBD. So, SBC divided by sine theta 6, SCD divided by sine of theta 5 and SBD divided by sine of theta 4, and this is what we want to find out in terms of S and theta angles. So, now using these two equations I can straight away write it. Let us see, first determine SBC. So, SBC is equal to sine theta 1 by sine theta 2 into S. Secondly, if I put this value here and then I can find out SCD is equal to sine theta 5 upon sine theta 6 into SBC, which is nothing but sine theta 5 by sine theta 6 into sine theta 1 by sine theta 2 into S. If I keep on developing such network of triangle, it will be very complicated and this keep on growing. So, what is the remedy here? I want to find out what is sigma SCD, what is this value? Given sigma x and all other variables, that is sigma theta 1, sigma theta 2 and so on, all the sigma thetas which are measured in the field are given. So, how can I find out this sigma SD? One way is to make this as a function and try to make the Jacobian matrix, and you know the process. But there is some intelligent process also, but it is called stepwise error propagation. First I will do sigma SBC error. I will find out by a simple relationship. If you just see the last one here, this relationship I use, let us say equation 3 and that is equation 4. So, equation 3 I will use. So, SBC is equal to sine theta 1 by sine theta 2 into S, right. So, there are 3 variables and I want to find out sigma SBC. Sigma SBC is equal to J sigma theta 1 theta 2 S into JT. So, matrix J is given by dou S by BC by dou theta 1, dou S BC by dou theta 2 and dou S BC by dou S. Well, you can calculate this matrix, then I can put this value and I can find out sigma SBC, right. I am sorry, here it should be square, right. I have calculated sigma SBC. Now, we will use equation 4, and equation 4 says that SCD is equal to sin theta phi by sin theta 6 into SBC. So, I write SCD equal to sin theta phi by theta 6 into SBC, right. This is the equation now. If I want to find out sigma SCD square, I can write that is a J sigma theta 5 theta 6 and SBC, right, into JT. So, what is the value here of J matrix? J matrix is, that is Jacobian, dou SCD by dou theta 5 dou SCD by dou theta 6 dou SCD by dou SBC. Now, again this is a 3 variable problem. Here I have already this value and I got this value. Okay. So, what was the value here? Sigma value in this case, let me just draw the two cases differently. Sigma theta 1, theta 2 and S, this was variance covariance matrix 0, 0, 0, sigma theta 2 square and 0, 0, 0, sigma S square. So, find out value here of sigma square SBC. Here in first step I find out sigma square SBC. Using this value of sigma square SBC, in the second step I will find out what is the value of this using this logic, where sigma theta 5 theta 6 and SBC will be there, and that is nothing but sigma theta 5 square 0, 0, 0, sigma theta 6 square 0, 0, sigma SBC square, and this value is nothing but this value. So, we have learned what is the error propagation, we have seen few examples, then we learned what is the stepwise error propagation. Now, we will see what are the real applications which are really required in the field in a project. And the first application is tree analysis that I am going to take today. So, what is the tree analysis? You have already seen in the basic surveying, so I am elaborating it. Let us see, this is a terrain and this is a tower of a, let us say, any mobile tower, I can say like this, something like this, or maybe you can make some crisscross. Okay, you want to find out what is the height of the tower from some benchmark value called datum. So, what is the height of tower? Okay. Or given the point A here with the height ZB, what is this ZT, top of the tower, you want to find out. ZB is coming from, say, map, a contour map. Okay. Now, you put a total station over there, this point at A, right, and then you establish a horizontal line of sight. Then you measure this height, this distance, let us say D, and you measure angle alpha, elevation angle and distance, that we do with the help of total station. Now, if you also measure the height of instrument, capital H here. Okay. So, let me write ZT is equal to ZB plus H plus D sin alpha. That is the ZT, you can determine it by putting these values, but what is the sigma square ZT? Now, you see that ZB is coming from the contour map. So, it is completely independent of the height of instrument, because you have measured the height of instrument with the tape and you have measured this one from the TS, this is you measured with the tape. Okay. All three sources are independent, they are not correlated to each other. I can write here sigma ZB square plus sigma H square plus D square cos square alpha sigma alpha square plus sin square alpha into sigma D square here, right. Okay. B here. Right. Now you see three sources are contributing to the error propagating to height of the tower with respect to some datum. Now someone says that I want to measure the height, or a client comes to you and say that I want to measure the height of the tower with respect to a datum, but this height error should be within some limit. Let us see a threshold of t. Okay. Here, let us say it is 10 centimeter or 5 centimeter, whatever. So what will you do now? Sigma zt, you can calculate it 3 times sigma zt should be less than equal to T tolerance, which is given by the client. Okay, so I am just saying tolerance here, and it is tolerance here. Let us take the next one, which is compatible measurement. Again, the matrix sigma L square, sigma LD, sigma D square in case of latitude departure example, this one, right? As we said, it is sigma LD. Here if you see that length measurement is very accurate, or bearing measurement is very accurate, and as a result of that I am getting some value of sigma L and some value of sigma D which are quite different, right? You see the expression and try to fit some inappropriate values and try to see what do you get, sigma L square or sigma D square. So it could be possible this is value of sigma L, right, like this, and this is sigma D, which is quite small, right? And that is why we say that if this is an error of the location, let us see 2 sigma D, I can say, and this is 2 sigma L. So this is a kind of error I am expecting in the location of a point which is given by L and D. Now what will happen, you see, I am wasting either a resource or I am trying to match two inappropriate resources. That means either I am doing length measurement so accurately that it is not compatible with the bearing measurement, or I am doing bearing measurement so accurately that it is not compatible with length measurement. Fundamental measurements are length and bearing, if you remember, in latitude departure calculation. So how can I do the proper selection of the bearing measurement instrument, that is compass, and the length measurement instrument, that is tape or total station? Idea is very simple here. Let us theoretically make them equal and try to find out the relationship between L and beta, and then you can fix specifications of compass which will measure beta angle, and you can fix the specification of tape which will measure the L. So what will you end up with? Some relationship between sigma L and sigma beta, right? So try to find out this relationship yourself, and then according to this compatibility measurement you can fix the sigma L and sigma beta, the precision or the quality or the accuracy of the instruments, tape and compass. That is a compatible measurement idea. The next is, what is the maximum error here? Again, take the example of the latitude departure measurement. Here we have sigma L square, sigma D square, sigma LD and sigma LD here, right. Now if I take couple of samples of length and bearing, then I try to find out latitude and departure for each line, and let us assume that each line is representing a sample. So I have length and I have a bearing of that line. So I find out for each line this one. Now if I try to plot those errors, let us say sigma L here and sigma D here. So since I have n number of lines, so I am trying to plot. This plot could come like this. These errors I am trying to plot, n number of samples, they are randomly distributed. There could be another possibilities like this, where they could be like this, n number of measurement. There is another possibility. Let us say this sigma L here and sigma D there. Okay, One more possibility is there like this, where n number of observations are like that. There is a clear linear trend I can draw between the two variables. Here I can see linear trend, but there is no trend here, right. So, in these two cases where I can observe the trend, I can say one thing, that there could be a relationship between the L and D, that means their errors are correlated. So, I can find out correlation between the two, that is the coefficient of correlation. Apart from that, I have one more query, what is the maximum error? Because it is elliptical shape, and I can see here that this error is maximum here, and here I can see that this error is minimum, which is across this. Moreover, I want to make errors such a way that these errors which are appearing now correlated, sigma L and sigma D, they should become uncorrelated. So, what can I do? Let us rotate this axis in such a way that this becomes new axis like this, and I call that, let us say, sigma L dash and sigma D dash. This is 2 times sigma L, and this is spread along D is 2 times sigma D. Then what should be the value of sigma L dash and sigma D dash, such that sigma L dash and sigma D dash are uncorrelated? And that is the principal component analysis, where the principal component analysis says that let us preserve the variances. So, what does it mean? So, if I do some kind of rotation theta here to the axes sigma L and sigma D, such that they become uncorrelated. So, what is the meaning here? If I write now after this L dash and D dash, it will be sigma L dash square, sigma L dash D dash here, sigma L dash D dash here, sigma D dash square. So, I can see here that if these covariances become 0, then I say that they are uncorrelated. If we do like that, in that case, first of all, variances are preserved. What is the meaning here? So, if I am adding sigma L dash square, sigma D dash square is equal to sigma L square plus sigma D square. That means I have rotated axis theta in such a way that the variances remain, but covariances become 0. Mathematically, if you see, I have shown you here, after rotation, this is 2 sigma L dash and this is 2 sigma D dash. One should write like this, not this way. I have changed the variances value, not the variables. So, do not do this mistake here. Let me just rewrite this thing again here. Yes, this is sigma dash and sigma dash LD. Remember, I have not changed my variables, I have changed only the variances value. Covariances are now equal to 0. Why 0? Because you can see that these two sigma L dash and sigma dash D are uncorrelated to each other, because they are along the major axis of the ellipse and the minor axis of this error data ellipse. So, they are uncorrelated. Okay. In this case, if I rotate by angle theta such that I ensure this property, in that case I can prove it mathematically that variances are preserved. At the same time, I find out the maximum error here, the maximum amount of error. So, this is the maximum value of the ellipse here, or the major axis, which is equal to 2 sigma L dash. So, that is the idea here. I find out the principal component, what we call. So, you can also find out what is the formula of the principal component. This is given by sigma dash is equal to sigma L square plus sigma D square. For 2D variable I am writing it. To the power 0.5. Okay. Similarly, here minus and the same quantity here, and try to find out yourself whether it is correct or not. We give the formula of theta like this. So, this is the principal component analysis, and here we stop, and with this idea we have finished our error propagation and the applications of the error propagation. Thank you.